Okay, my name is Jack Purdum. This is Al, my cohort. And we've been working on this radio that you see on the stand over here. It's a software-defined radio. It's rated at 20 watts. It's not portable. We call it a trunk portable. It weighs probably around 10 pounds. So
I'm Jack's fan.
yeah, I tried to do better, but this is what I got. So anyway, one of the things that we've done with this, we've put an encoder, decoder in it that most of you probably, how many know CW? Okay, that's what I figured. What we're trying to do though, is encourage other people to learn CW. And I think the Coke method is the way to go. And if you're familiar with the Coke method, it has, you pick a target speed like 30 words a minute, and then you add a Farnsworth delay, which maybe is at 10 words per minute. So you get a character at 30 words a minute, but you have a delay between that and the next character of 10 words per minute. So you listen for the rhythm. 30 words a minute is fast enough, you can't count dits and das. Instead, you have to listen to the rhythm. So we think that having a decoder in this radio might encourage some people to practice and learn CW. Now, I've written decoders before, but Al came up with some really clever ideas, and we've named it the ALP decoder, and that's for Al and Purdum. Now I'm starting to think it should be PAL, but we haven't decided on that yet. But anyway, Al came up with some very, very clever stuff for the decoder. And as much as I'd like to take credit for it, he's right here, so I can't do it. Okay, this is a picture of what you see up there. This one though has a 5-inch screen. This one has a 7-inch, and it can take a 9-inch. It is not a touch screen system. The screen is capable of touch screen, so if you wanted to put touch screen in it, you probably could. But you see all of those switches over there? Those control almost everything that you're going to need to do with the radio with one push of a button. And some of you are going to say, well, that's kind of stupid because you're chewing up 18 pins from the processor. That's not true. We're controlling 16 of those pins with one IO pin. And it works very well. It's just, we're reading an analog pin, but we have a voltage divider ladder, and just read the pin presses or the button presses that you've used. Okay, that's what it looks like on the outside. And then a peek inside. Actually, I'm just kidding. This is exactly the same slide that Steve had this morning. And Pete Giuliano is a friend of mine. And if you don't know Pete, Steve told you that he's an inveterate home brewer. And that's actually selling Pete short. You could take Pete, strip him naked, give him a stick and set him into the woods, and he'd come out 2 weeks later with a kilowatt transceiver that ran on creek water. He's an extremely talented guy. So anyway, I got his permission to use it. Steve, did you get his permission? Okay, these are the general features of the transceiver. We call it fuzzy QRP because it is capable of 20 watts of output. And actually, Al's run it up to 35 watts on 80 and 40, but we're calling it 20 watts. And it does maintain the 20 watts all the way through 15 meters. 10 meters drops to about 12 to 13 watts. The nice thing about it is it's completely self-contained. No PC, laptop, or tablet is needed. All of the IO is done on the screen that you just saw. Trunk portable, I mentioned it's not lightweight, but it's something that you could throw in the trunk of your car and take it on vacation or something like that. Reasonable cost. When we started this project, it probably cost, this was 2 years ago, it probably cost about 150 to build fresh components. I'm afraid now it's probably 250, just because of part scarcity. And everything is open source. Late next week, we will have the Gerbers for all the PC boards, the BOMs, the schematics, and all of the source code will be available on our website. And that's website is called Software Controlled Ham Radio. And if you buy the book, if you have the book, or just look up Software Controlled Ham Radio and you'll get to it. Okay. We wanted to create a platform that could be expanded and experimented with. And for that reason, the EP in the T41-EP stands for Experimenter's Platform. All of the boards are 100 by 100 millimeters or less to take advantage of the PC board houses reduced prices. And there are 7 boards. So if you don't like our Exciter board, rip ours out, put yours in, and off you go. Learning tool. We became painfully aware a couple of years ago that the DSP information that you really need to make a transceiver is scattered all over the place. So one of the things that we did was in the book that we wrote is to bring all of that into one place. And we think we've done that. Learning Morse code, I've already mentioned. We think that this is a good vehicle for doing that. Why learn Morse code? First of all, you all know it's efficient. Miles per watt's pretty tough to beat. And there is a Japanese guy who earned DXCC with 500 milliwatts. What he didn't tell you is he's on the 60th floor of a townhouse in downtown Tokyo. And that's true. We feel that this is capable of being the main rig for someone who's on a lawn mowing budget, doesn't have a lot of money and wants something that's fairly inexpensive yet viable. The UK was interesting. They did an experiment and the big draw was CW. And the reason was because then their parents couldn't understand what they were saying. There is self-satisfaction on building something yourself. There's also self-satisfaction of using CW. Most of you know that. It is a challenge. I'm trying to get to the point where I can close my eyes and copy at 30 words a minute. I've got a ways to go. And CW can save your life. If you're trapped in a submarine, you can take a wrench out, tap on the Morse. What? It could happen. Okay. The decoder should, you would think, especially having written 3 or 4 decoders before, you would think it would be a fairly simple process, but it isn't because things go wrong. First of all, the assumption is that everything follows a 1-3-7 timing. The vertical lines, whoops, sorry, wrong button. In between each one of those vertical lines is one space. So that would be the 1 of the 1-3-7. Dashes, 3 of those units. A word is 7 of those units. The problem is no human sends perfect code. Okay. So the decoder then has to cope with these differences that deviate from the 1-3-7 timing. Straight key, you would think you would have all control, but everything is up to you. And if you've ever heard someone using a straight key, there's no hiding that they're using a straight key. It's very easy to tell it, at least I think it is. If you're using a bug, you still have control over the spacing for intercharacter, and you also have word control spacing. Electronic keyer, you still control the words and the intercharacter intervals. All of these factors factor together to form something that we call the fist. It wasn't that funny. The fist is a combination of all the factors that make your CW different than everyone else's. First of all, decoding problems, incoming signals are not ever uniform. This was an actual plot that we took off of the SDR using the Arduino IDE. The Arduino IDE, if you're not aware of it, has a plot function. And this plot, this plot was once again taken from that. And you can see down here, there's probably a signal, but we don't know what it is. We can reduce the magnitude of those problems by using a larger scaling factor and then clipping the signal. And that's what we did here. And as you can see, this I think is clipped at a value of 4. We multiplied it by a scalar, which I think was 10,000. And then we clipped it at 4, and you get these nice peaks. And this says it for E in Morse code. But there are still going to be some problems. It seems like it would be simple to just read the dits and dots and decode it, but it doesn't work out that way. There are different elements of figuring out the spacing problems. A through B, AB length is what we call a dit length. CD is a DA length. BC, we don't know. And the reason is because it could be an intra-character spacing, or it could be a word spacing, or it could be what I call an atom spacing. In other words, the spacing between a dit and a da and the letter A. So you have to figure that out as part of the decoding process. We don't know what it is. We can only test that empirically. Other nasties, noise. What is that right there? Are we looking at a spike? Is it something local? Is it a wiring spike? The air conditioner went on? We don't really know. And then you've got these guys that are coming up close to being something, but they don't quite make it. You have to cope with those. QSB, this is an actual plot of a signal. And if you have a cutoff, you can see that some of those signals are cut off before they reach the peak that we do the clipping. And that makes decoding it an issue. And then there's just plain hiccups where you just don't know what went wrong. Right there, signal dropped out, a glitch, no predicting what that is. Okay, Al's algorithm. Might have you vote on this Al thing, I don't know. First of all, we have to fine tune the CW signal. Hans has a very good decoder in his QCX family of microcontrollers. And we use the same one that we have for years. And what we do is, if you look at the, I don't think I have that slide here. One of the plots that we have is an audio plot. And this is being plotted from about 4 kilohertz down to nothing. And we are centering the sweet spot at 750 hertz. So we're trying to set the audio peak at 750 hertz. And once we do that, it is tuned for the optimum performance by the Gertzel algorithm. So we have that. We put up the 2 lines, and when you're listening to a CW signal, you can tune that in, and those lines then will center on the audio peak. What we can't show in real time here is you can also set this upper limit, and there's a lower limit here that you can set to compress that CW filter down as narrow as you want it. I think 100 hertz. Okay, what?
There's also, in the CW mode, there's also a specific filter.
Yes, 750 hertz. And well, and that's tied to the algorithm. Yeah. Okay, well, I tied it in code. I find. So, okay, what's a dit and what's a da? We did pretty extensive statistics on sampling. This, believe it or not, is the code timing for one person sending for about 10 minutes. And we think it was with a hand key. I'm pretty sure it was. And you would expect, if someone is sending code consistently, you would expect bimodal distribution, a dit length and a DAW length. And as you can see here, the dit length is pretty uniform, but there's lots of noise down here. The problem is the DAW length is almost perfectly bimodal. So what we have to decide is, are we hearing a dit or are we hearing a DAW? And we do that with timing. In other words, how long has this signal been running? So somewhere between here, we can say, okay, everything above this mark is a DAW and everything below it is a dit. Well, the thing to do that is the hypergeometric mean, because it tends to squash outliers and it will cluster more. So what we do is we take a very quick calculation of the hypergeometric mean, and we use that in determining what a dit and what a DAW is based on their timing. Now, there's a tendency to think that this takes a lot of time. Actually, we're running on a TNC 4.1, which runs at 600 megahertz. So as far as microcontrollers go, well, the Arduino Nano is at 16 megahertz and we're at 600 megahertz. So for us to catch up with the Morse code is usually 2 or 3 letters, and we've caught up. So the lag isn't too bad. The next issue is noise. What constitutes noise and what constitutes signal? We define noise as anything random that doesn't contain any information. Anything else is interpreted to be information and a signal. So what we have to do then is find a way to accurately assess whether we're listening to noise or are we listening to a signal. And to do that, we do a correlation analysis. In other words, we want to correlate the signal that we're receiving with the state that we think we're observing with respect to dits and DAWs. So what we're saying here is, if we get a correlation above 1.5 or 0.15, we're going to call it a signal. Anything below that, we're going to call noise. Okay, and here's what happens. Whoops. If these are the raw signals, those jagged things, and what we're doing now is we're saying, okay, since it's above the correlation coefficient of 0.15, we're going to call it a 1. So we immediately take this signal, multiply it so it comes up to 1. If it doesn't meet that, we're going to call it noise and just let it get buried in itself. So then by doing that, we end up with some really nice peaks and valleys, and the signal, even though it's jagged and doesn't lend itself directly perhaps to decoding, by doing a correlation analysis on it and rejecting the noise that way, we actually improve substantially the information content of the signal. Okay, the Gortzel algorithm I told you about before, it's used to take the signal and compress it down into a sweet spot. We've set that to be 750 hertz, which isn't a bad side tone actually. And then we can apply the Gortzel algorithm to that to decide whether we have a signal or not. This is kind of a busy, I'm not sure how to explain this. You can see going across here where we've clipped it, okay? And this up here is the raw signal. But inside of that is buried the correlation coefficient that ends up with this signal. The green line here, what's the green line now?
That's the combination.
That's the combination of the two.
That's the combination of correlation. Narrow band.
Right. And then we can use that to interpret. I've got a more of an explanation of that in the.
Yeah. One point on that.
Yeah.
The reason that's important is the threshold that you get up here is if you just use one of the methods. So for instance, you just use the Gurtzel, you'll get something that will give you a signal noise ratio of this amount. So that the discrimination that you get is improved when you have a combination of correlation between the input signal and 750 hertz with the Gurtzel. So you get an improved signal to noise ratio. So in other words, you get an ability to dig out a little bit more of the signal from the noise using this combination.
Okay. So what the ALP decoder does is it takes the Gurtzel filter, we do the scaling and the clipping. We use the hypergeometric mean to divide whether we're listening to a DIT or a DA based on timings. And then we apply the correlation analysis. And then we can decode the signal itself. Then once you get the signal, that's all you've got. You don't have it in an ASCII equivalent that you can pop up on the screen. So we have to then decode the DITs and the DAs to the appropriate letters rather. We do that using a binary tree. A binary tree, everyone's heard of this. They don't perhaps think of it that way. But on The Price of Right, if you've ever watched that show, you have to guess the price of an item. And the host will tell you whether your guess is too high or too low. So if, let's say it's a 60-cent item and you guess $1. He then says too high. Now note what that does. With one guess, you've thrown out 39 possible answers. So then you guess below that. So you have it, you would guess 30. And he says too low. So now you can throw out everything below 30. So in two guesses, you've thrown out about 70% of the numbers. So we use this binary search approach then to decide which letter we're actually listening to. These are the rules for the binary search. If we hear a DIT, and we can tell that because of the histogram and the DIT timings, we know whether we're listening to a DIT or a DA. If we get a DIT, we go to the left of the current point in the tree. And if we hear a DA, it moves us to the right of that. A DIT increases the array index by 1, but a DA increases us by the binary index that we're at. You'll see this in a minute. The starting binary value is equal to the number of elements in the decoded array. Okay, now, this is the binary tree. You start here. And for sake of argument, let's say that we've had the letter A sent to us. That would be a DIT and a DA. So we hear the DIT, we know it's a DIT, and the rules that I just showed you said if it's a DIT, we move to the left on the tree, one level. So that would take us down to here. If we then hear a DA, that says that we move to the right one level, but we add the binary code for that movement. So we're going from 1 to 17. Okay? Hello? Okay. Now, if you look down here, I've coded this so you can tell where we are. Uh-oh, that's not good. What'd I do?
You went all the way to the end.
Okay. There you go.
Right there?
Yep. Okay, I'll try this again. So here we are with the DIT and the DA, it's the letter A, and that should be the 17th element in the array. And if you look down here, you'll see A lines up above the 17th element in the array. I've put a little scale down here so you can see where we are. In the actual code in the T41, this is a 128-bit wide tree because we've also added some punctuation marks. And so we need to be able to have 128 cells in the array. So now, what if you got an N? So you start here, it's a da, so you move to the right, you've come down 32. So right here, you would have 32 for the first da. If they quit there, element 32 should tell us that it's a T, which it does. But since we've got a dit coming in afterwards, we go to the right, that's only a 1 index jump. So we would then go to element 33, and we look at 33 and it's an N. By doing this back and forth, dits and das moving left and right through the parse tree, you can actually end up then with the ASCII character. Then what we do is once we have the character, and we can tell that we have the character because of the spacing between characters. If we get a 3-atom space with no signal, we know it's the end of a letter. And then we can then pop it up on the bottom of the screen. And this shows down here what we're decoding. And evidently this was at about 24 words per minute. This isn't exact, but it's pretty close. This is the sweet spot I was telling you about. And this box lights up if you're in the sweet spot. So we've got 2 clues to tell you whether you've got this thing zeroed in or not. And once you do, it works fairly well. Okay. If you build this or if you implement this algorithm, one of the first things that you're going to do is you're going to test it against W1AW. And W1AW sends as close as you can get to perfect code, the 137. It's not generated with a fist. In fact, the code from W1AW has all the personality of a stick. But it is good practice, okay? Below 18 words per minute is that Farnsworth delay I told you about earlier. So you have to get above 18 words per minute to get the 131 timing or 137 timing. Below that, it's dependent on what they've set the Farnsworth timing to be. The ALP algorithm makes no attempt to decode the Farnsworth stuff. And the reason that we don't do that is because we don't think anybody sends Farnsworth delayed code during a conversation. The other thing that is wrong with W1AW as practice is you don't get the flavor of the abbreviations and the common sequence of a conversation on CW that you do from just listening to the radio. And so we're hoping that what happens is people will build the radio, tune in a CW station, turn on the decoder, listen and watch, and learn Morse code that way. Our goal is to get more people using Morse code. No one uses perfect 137 timing, and therein is the difficulty and the hard part of doing a decoder. Performance is dependent upon the consistency of the decoder, of the sender. If you watch this decoder over, say, a 20-minute QSO with somebody, that timing thing that you saw at the bottom where it said 24 words per minute, that can go from 20 to 25 down to 18 up to 28, depending on how tired the person's getting. Your speed changes enough for the decoder to sense that you're getting tired. And that can make it difficult to decode. How to improve the ALP decoder and performance? Have your sender send perfect 137 timing. Use 1.5 kilowatt transmitter with a Yagi that's pointed at you. Then all of that goes away. In fact, you could probably just count the RF balls of fire that. Questions? I'm bringing Al up because he's the smart one. In the back there. Okay. The question, I think, is cell phones and other devices like that have the ability to correct misspellings and things. Well, first of all, that wouldn't work real well because hams use so many abbreviations. ES, what's it going to do with that? It's not going to translate it to and. But the other problem is the resources. For example, is it FLDigi?
Yeah, I know, it's the other one online. Give them-
One of those actually has a word lookup. And if you misspell a word, it'll correct your spelling. But that runs on a PC, if I'm not mistaken. And we don't have the horsepower, perhaps, to do that kind of sophistication.
Yeah, use your.
We looked at that. There's plenty of resources in the Teensy to incorporate one of those lookup tables. And you could even put in it the abbreviations if you wished. We haven't done that. That's one of the things that we suggest might be a very good project for somebody who wants to do the EP part of that experimenters platform. So if you're so inclined to do that, please do and let us know how it turns out, because it would be a good addition.
The other thing that I neglected to say was the code that is behind the T41 is using about under 3% of the available flash program memory. So you have about 7.7 megabytes of free code space to add things that you want to add to it. So, I mean, we're doing a lot in what, 300K? So there's plenty of space for enhancements. And in fact, the last chapter in our book says enhancements that either we'd like to try later on or other people can try for themselves. Anything else? Yes. I think you could. No, but that would be an enhancement you could add. Yes. Not that I know of. Bud Churchward has a kit out there that is a decoder, has a decoder built into it. And maybe Bud would take this code and put it in his device. We have no plans for it since we've sort of got it built in ours. But unfortunately, you have to build the rig to do it.
Now, one of the limitations would be that you have to use a processor that is capable of running some fairly sophisticated code. So we have digital signal processing that uses a fair amount of resource. And that's why the Teensy is 4.1 running at 600 megahertz is the microprocessor of choice. This code would not do very well on any of the 16 megahertz Arduinos as it stands. So that would be somewhat of a limitation, but the state of the art has gotten to the point where these microprocessors are quite available and they're as easy to program as any of the Arduinos. So that should not be a real practical limitation for anybody.
Well, also all of the work, all of the code that we wrote in the Arduino IDE because we didn't want to take advantage of any JTAG debuggers or anything like that. We wanted to do it all under the same limitations that most of the experimenters would be using. Yes. Yes, there is. 5 words per minute was the old novice test. And a word at that time was considered to be the word Paris. Paris has 50 atoms to it, if you will. And they use that to come out with that formula that is words per minute equals 1200 divided by the time in milliseconds. So you can flip that around and you know that 80 milliseconds per character turns out to be 15 words a minute. So that's the standard formula for calculating that. We're off by a little in calculating the words per minute. I know we are, but part of that is probably because of the time that we're taking to do some of the calculations.
One of the things that's critical about, or not critical actually, is our algorithm does not take, let's say, the words per minute as a limiting factor. We calculate the words per minute. We don't use the words per minute to determine the timings. The timings are determined from the actual data and on the fly, adjustable or continuously updated histograms based on the actual measured timings. And that's one of the things that Jack mentioned, somebody getting tired. Well, the algorithm measures the timings and it adapts. So if your timing changes over a period of time, slowly or even fast, the algorithm will do that and adjust accordingly.
Yeah, we call that adaptive coding, and we can catch up usually in 2 to 3 letters, even if there's an abrupt change in the timing. You had a question? Pretty fast, typically 2 to 3 letters.
Yeah, it depends. If it's all the same operator, it goes pretty quickly. If you've got a QSO going and the guy on the other end, even though you can get the signal very nicely, it's strong enough, his frequency may be off a bit. And if it's off too much, what you're going to end up with is the very narrow Gertzel filter that we have in there won't put him back in the sweet spot. So you have to do a little bit of tuning. Now, one of the things that somebody could really do if they wished was to do an adaptive update on that. But that's a fair amount of coding. The horsepower is there to do it. It's just a matter of getting an algorithm that works.
Yes. Well, the first question was, have we any benchmarks to judge the performance? And the second part was, have we done any benching against like contests? And I think most of the contest guys are using mechanical recordings of their CQs and so forth. No, to be honest, we haven't done that. It would be very easy to add the CW messaging feature in. In fact, I think I have provisions for that. I just haven't coded it yet. But no, I have not benchmarked it to any extent. Yes. Well, we're really pretty happy with this. Like I said, we've spent 2 years on this, and we think it's pretty much there. Now, we do have things that we would like to add. For example, I really think it would be possible with the decoder to actually have it do a CW log entry during contests, where it would log the person's call, the time, frequency. And there is built into the T41, there's a SD card carrier. So you could just shove the SD card in there. We already have a connector coming out the back that will read from the chip. So somebody could write the code to actually do an ADIF file.
Yeah, there are a couple other things just along the same lines. The Teensy has the capability of running 2 USB ports simultaneously. And we have a provision on the main board that brings out the other USB. So you can put a keyboard on there, or you could put a mouse on it if you wanted to, or some other device. And so that's something for the future. There are lots of things that we're looking at, we'd like to add, but it's a matter of time.
We're getting old. I don't know how much sand's left in this old clock, so
Way in the back.
way in the back. You know, Norm has that information, or David rather. The four-state QRP Club is looking at putting together a kit. And what they are going to offer, unless plans have changed, is a semi-kit where all the SMD parts are soldered in place. And by the way, the Gerbers that'll be released next week do have SMD parts on it, but it's the 1206 parts, which are the pretty big SMD parts. So even I can handle the SMD soldering with no problem. Anything else? We're getting ready for letting all this crap go next week. No, actually, I think both of us have little dinky projects. Al and I started a builders club in Cincinnati, and one of the things we're going to do is just build a little Ballonford end wave, half wave end fed antenna, build it out at a park, and then throw some wires in a tree and try and make some contacts and then have a picnic afterwards. That's about as far as I thought. Yes, sir. At 0.00875. Oh, we never ran the demo. Oh, run the demo.
Sorry.
This is just to show you that. There is no sound. This is
Oh, there
just,
is no sound?
no, I don't think so.
Okay.
This is just to show you that we didn't make all this up.
Not us talking.
By the We have one at 35 words a minute too. We didn't bring that one.
Bandwidth was 3,200 hertz.
No.
Your pass band,
Not for CW.
your pass band was 800.
Well,
That,
go ahead.
the 3200 is showing what you'd normally get from SSB. Over here. For CW only, we have a special filter that, let's go over, Jack. There, so everybody can hear, see us. For CW, we have a very special digital signal processing filter that has a bandwidth of about 200 hertz centered on 750. That's in addition to the Gersel filter, which is a very narrow band. But the objective there is to be able to pre-filter it and get rid of some of the other noise. Now, what you're hearing when you're tuning is you'll hear the whole signal. So as you're tuning it, what you do is you tune through the signal and it'll start out at high or very low frequency until you finally get it up to the sweet spot. So we don't turn off the audio. If you use the other filter, that's in addition, and you can actually reduce the overall bandwidth. So as you're listening to it, you hear the high frequency starting at 3.2, but it only actuates the CW decoder when it gets within the bandwidth of the 750 hertz signal. So one of the things about this receiver is that with the DSP and being code-based, you can make all kinds of changes in this thing. So if you don't happen to like 750 hertz, there are some other frequencies that will work well. You could do it at 900 some, you could do it down about 600 some. We haven't made that as an option as yet, but being in code, it would be very easy to change that and make a menu item that you could say, well, I really like the side tone of this or that or the other, and do that. It's another project. It depends on how important this is, how high on the priority list, and it hasn't been one for us. We wanted to get the decoder to work, which we did, get the rest of the receiver to work. So there's a list of projects that could be done, which is pretty long.
That's where the decoder right there, as you say, the sweet spot. Multiple people sliding grit to move them, move them off. Well, by the sweet spot means that we're optimum decoding. We can decode outside of the sweet spot.
So, for instance, if it's within,
If the signal coming in is within 100 hertz of the other guy, it's okay. If you're 500 hertz off, then you're out of the sweet spot. But hopefully these guys have got their modern rigs that'll be fairly consistent in the frequency. Yep.
Also, keep in mind that we can do split. So if these guys want to go far enough away, have them go far enough away. Yep.
You showed this in Ozark.
Right.
We were there, and we were stepping the code. Were you able
Yeah.
to reduce that to-
Well, you can set the increment, well, really anything, but we have it set from 10,000 down to 10 hertz.
Okay.
And there's a button on the bottom left that is the increment. And you just push that and it changes.
Well, I didn't catch that one.
Yeah, no, yeah, that's fully adjustable.
No, no.
Well, there's an array in there that right now has the values 10K, 1K, 500, 250, 110. And you could make that bigger or smaller.
You can make it one hertz at a time if you want to.
Yeah.
You'll be forever turning the knob, but you can do that. Anything else?
Okay. I don't think there is. It's a matter of personal preference. For me, I like 700 hertz. I have a friend of mine, Dave Vest, who likes 600. So I think it's just personal preference. But as far as performance would go, it doesn't matter. Okay, well, I better let the next person talk.